Welcome back to another explainer brought to you by Forge College. Today, we're tackling Implement Coding Vesting Schedules, which is a crucial part of our Vesting Schedules and Token Sales module, right inside the Building Token Sale Mechanics section of your Applied Solidity development track. Now, if you remember our last lesson on aligning tasks and monitoring for deployment, we laid out the high-level roadmap. But today, today we're getting our hands dirty. We are shifting gears from pure tokenomics theory to actual functional Solidity code. This is exactly where the magic happens. And, by magic, I mean that terrifying reality where a single tiny typo could literally lock millions of dollars in the void forever. But hey, don't sweat it. We're going to build this step by step so that doesn't happen.
We all know the math behind a vesting schedule looks beautifully simple on a whiteboard, right? But teaching a smart contract, a completely unthinking, rigid machine about the passage of time, that requires a meticulously drafted blueprint. You see, math assumes perfection, but code is messy. It has to deal with the harsh realities and constraints of the blockchain. So let's bridge that gap and build ourselves a flawless vesting machine.
So here's how we're breaking it down today. 1. From math to code. 2. The beneficiary blueprint. 3. Calculating the vested amount. 4. Releasing the tokens safely. 5. Simulating time for testing. And finally, 6. Next steps for integration. Let's jump right in.
Section 1. From math to code.
Okay, think about this for a second. How do you actually teach a smart contract about time? The Ethereum virtual machine is, quite frankly, chronologically challenged. It's kind of like a machine locked in a pitch-black room that only knows what the current block timestamp tells it. So we have to be incredibly explicit. We need to map out exactly how elapsed time translates into vested tokens within our contract state.
As a quick refresher, we're dealing with two main concepts here. First up is the cliff. A cliff is basically like a highly anticipated video game launch date. You absolutely cannot play before midnight, no matter how much you mash the controller. Then you have linear vesting. Once you finally get past that cliff, linear vesting is the steady, continuous drip of unlocking tokens over a set duration.
Section 2. The beneficiary blueprint. To make this work, we encapsulate all our data into a single struct. Think of this beneficiary struct as a digital punch card. It keeps track of the total allocation owed, what's already been paid out, the exact start time, and the specific seconds that dictate both the cliff and the overall duration. It's neat, it's tidy, and it gives the contract literally every piece of context it needs in one perfectly packaged bundle. Section 3. Calculating the vested amount.
Now, there's a really important distinction we need to make here. We've got the vested amount, which you can think of like an hourglass. It's what you've earned conceptually, purely based on the sand falling over time. But then you have the releasable amount. Think of that like an open vault. It's the actual tokens you can safely withdraw right now, after subtracting any previous withdrawals. It's exactly like the difference between your gross salary on paper and the net take-home pay that actually hits your bank account.
And that brings us to the big, fat zero. You've got to remember the golden rule of the cliff. If the current block timestamp is even 1 second before the start time plus the cliff, our contract's calculator strictly returns 0. No exceptions, no fractional rounding. The gate is firmly locked until that exact cliff timestamp is reached.
Section 4. Releasing the token safely. Safety is absolutely everything when we're writing smart contracts. That means we have to strictly follow the checks, effects, interactions pattern across 3 very specific steps. First, you compute the releasable amount. That's your check. Second, you update the state by increasing the released amount. That's the effect. And third, you actually transfer the tokens. That's the interaction. Whatever you do, do not mix this order up.
I'll say it again because it's absolutely crucial. You must always update the contract state before making the external transfer call. It's just like checking your bank balance and updating the internal ledger before handing physical cash over to a customer. If you hand over the cash first and something interrupts the system, say a reentrancy attack, the ledger might never get updated, and boom, you've got a double spending nightmare on your hands.
Section 5. Simulating time for testing.
Obviously, a blueprint is totally useless unless we prototype and test it. Using local development environments like Hardhat or Foundry, we can actually play God and fast-forward the EVM timestamp to test exact moments in time. Since Solidity uses integer division, which completely truncates decimals, we're looking for precise whole numbers here. For example, at day 15, we expect exactly 0 tokens because we haven't hit that 30-day cliff yet. But at day 90, exactly halfway through the schedule, we expect exactly 500. By simulating these specific timestamps, we prove that our math holds up in the real world.
Visualizing this timeline in our tests guarantees 3 massive things. Number 1, the cliff strictly blocks any premature withdrawals. Number 2, the mid-vesting phase pays out correctly and proportionally. And number 3, the schedule caps out perfectly at the total allocation at the end of the duration, guaranteeing that absolutely nobody gets overpaid.
Section 6. Next steps for integration.
So we've successfully built a reusable, rock-solid pattern. By separating the cliff-gate logic from the linear accrual math, we isolate these behaviors so they can be tested rigorously and safely. This kind of modular architecture, that is the absolute hallmark of top-tier smart contract engineering.
But now that you've mastered this isolated vesting logic for a single user, what's next? Well, the final boss is taking this perfect little machine and integrating it into a massive aggregate accounting system for hundreds or even thousands of beneficiaries. How do we manage that kind of scale without breaking the gas limit? That's exactly what we're going to tackle in our very next explainer.
To keep pushing forward in your applied Solidity development track and to master these Web3 mechanics, head over to forge.college and explore our complete library of resources. This explainer was brought to you by Forge College. But hey, before you log off today, ask yourself this: what actually happens to this perfectly isolated system if a beneficiary's wallet gets compromised halfway through a 10-year vesting schedule? How would you code an emergency stop? Think about it. Thanks for hanging out with me today, and I'll see you in the next one.